Okay. I think we should make a start because we've got a lot to get through today. Can you hear me at the back? Is the sound reinforcement's working? Okay, good. This is a very big claim. I know this, and I know that I have to prove to you that I'm as good as my word. So I'm going to make you a promise. In the first 10 to 15 minutes of this talk, I'm going to convince you that this is true. It's going to take me the rest of the talk to show you how to do it, but I'm going to show you why this is true. That was a slide they made me put in. Now, let me tell you what the history is behind this, this talk and this stuff. I was working on a code base. This was a few years ago now, which was absolutely dogged with bugs. It didn't matter what we did with it. Every time we tried to knock one down, another one popped up. In order to try and take control of this was about 2.5 million lines, right? So it's not a major program. But in order to try and cope with this, we decided that we were going to delete our bug list and just see which ones popped back up again. Within 6 weeks, we had a list of 4,000. So that gives you an idea of what the problems were. So everybody was saying, how do we get rid of these bugs? And I thought, actually, there's a more important question to ask. Where are the bugs coming from? Not how do we get them out, but how are they getting in there in the first place? So this is what we found. This is basically the scale of the problem that we're working with. What we found was that when we looked at the bugs, when we went back through the version control, when we looked back at every fix, when we looked back at every bit of history, going back about 5, 6, 7 years on this whole project. It was a bit patchy in the beginning, but we had about 5 years of data. What we found was that the bugs fell into a certain number of categories. Basically, there was a bugged pattern that kept on showing up over and over again. It was the same one every time. Now, there were some bugs that were there just because we hadn't understood what we were trying to accomplish, or there were bugs that we hadn't understood the frameworks that we were working with. But fundamentally, 90% of our bugs all were of the same pattern, all were of the same type. And they're all there because somebody was putting them in. And I thought, aye, that's interesting. Can we understand that pattern in more detail? And it turned out that yes, we could. What we did next was we then drilled into our data in more detail. We said, well, can we find the bugs that were put there and were discovered at the moment they were put there? And can we find second-level bugs? These were the bugs that were introduced as a result of some other bug fix that was going on. And this is what we found. These primary bugs, they were about 90% of the total. The secondary bugs were about 99% of the total. Basically, what we saw was that our entire technical debt was being caused by one single anti-pattern. Now, I don't know how many of you have read The Mythical Man Month, Fred Brooks, absolutely classic book. One of the things that he says is that when people work on bug fixing, they find every team has about a constant bug rate. It might be 1 bug per 1,000 lines, 1 bug per 4,000 lines. If you're really unlucky, it's 1 bug per 50 lines, which is kind of what this was running at. But the point is, it doesn't matter how much fixing you do. This bug rate stays constant. And one of the things that he was asking was, well, is it because all of those bugs are already in there or because we're introducing them? Well, what this data showed us is because we were introducing them. Every time we fixed a bug, the nature of the bug fix introduced new ones. So pretty much 100% of our technical debt was caused by this one anti-pattern. I bet you want to know what this is. And I'm going to tell you, but not right now. First, did this work? First, we need to talk about this chap. This is Edgar Dijkstra. Edgar Dijkstra was a very clever chap. He was a computer scientist before there was even a word for computer science. And an awful lot of what we take for granted today, this guy invented. Back in 1968, he looked like this, much, much younger. And he wrote a letter. He was famous for writing these letters. He would send them off all over the place. They're all collected now in a library and numbered. But he wrote this letter, a case against the go-to statement. This was back in 1968, and he wrote it to the communications of the ACM. And in it, he said something which for the time was very revolutionary. He said he has noticed that the more bugs a program has in it directly correlates with the number of go-tos the program has in it. And he said go-tos cause bugs. This is his paper, the case against the goto statement. And I'm going to explain more about what's in this paper because it's a short paper, but it's fairly heavy computer science. But what he did was he explained not just that this correlation is true, but he explained why it was true, and he explained what to do about it. Anyway, he sent this off to the CACM, which was being edited by Niklas Wirth, who was the guy behind Pascal. And Wirth said, great paper, lousy title, let's do that to it. And the rest, of course, is history. And you can look it up online right there. Now, what does he actually say? Because the principle behind this paper is actually pretty important. He said that when we look at a program, then what we describe on the paper, when you talk about a program, we talk about a thing, right? It's, you can print it out on paper, or you can put it on a stick, or you put it on a server, or something like that. But we talk about it as if it's a thing, right? But what it actually is not a thing at all. It's something quite different. So what he said was that the program looks like a static map. It looks like, it's fixed, it's on the paper, or it's fixed on the screen. But what it means is a dynamic process. It orchestrates all of the processing that's going on inside a computer somewhere. But it makes no sense to have a static program because the program inside the machine is inherently a dynamic thing. When we talk about a program, the language that we use is this sort of spatial static language. So we talk about right here, this line here, such and such has happened. Or what about this variable here, or this class over there? And even when we're talking about class structures which don't even correspond to things on the page, we will actually gesture into space and we'll say this class over here, and it's, the data's moving like this. All of our language is spatial and static. And yet, the program has no concept of that at all. The program's concept is of time. The building blocks of a program inside the machine, the real thing that it represents, is actually a sequence of instants, one after another. Now, as people, as human beings, we are really good at understanding this spatial stuff. We're good at following maps, we're good at finding our way around cities. Compared to other animals, we're very good at it. So it's natural that we use this language. But as humans, we are really bad at understanding this. We all hate change. Even if you don't admit it, you hate change. But you find that when you put people into geographies which are moving all the time, they get lost, they can't find their way around, they actually feel sick because people don't understand this sense of change. So what we're trying to do is control something which is inherently dynamic and changing, which we don't understand, using something which is inherently static and locational, which we do understand. And no wonder that's hard. So what Dijkstra said was this. If this has worked, yes, it has. He says what we need to do is we need to find some language. There's no point getting rid of this because this is how we think. But can we find some language in which we can express both of these concepts at the same time? He called it an execution coordinate. So he said, can we find something that we can speak about which not only has this static spatial feel to it, but even while it's static, also expresses this dynamism. And what he came up with was an execution coordinate. And the execution coordinate lies at the heart of what we now know to be structured programming. So let me explain this. Let's take a really simple program. Can you read this at the back? Because I normally have real problems with the projectors and being able to see this. What we have here is a really simple program. It's the kind of thing that you've seen time and time again. It's probably one of the simplest examples of anything that you're going to see at this conference. Now, we can look at it. This is, I'm pointing to it. I'm saying, here's the program. Here's line 13. I'm using this static language, right? But what we can do is we can animate this program. We can say what happens when it starts to move. And what we find is that it executes each line in turn. And as it executes each line, we have this sense of line. But it executes each line at some instant in time. What we've got along here is this time axis. So, and what we've got, what this picture shows us, is a correspondence between the location in the program and an instant in time. So in Dijkstra's terms, this is a good execution coordinate because the one thing, say line 13, represents both the position in the program and that instant in time. So that works. Okay? Now, I want to explain in a bit more detail what his concept of an execution coordinate was. So we're going to animate this again, and we're going to stop it at line 13. So we've stopped our progress through the program, but we've also stopped our progress through time. We've stopped time. And we can see that we have this sense of being at line 13. So we can say, here is the location of the, here is where we are. Here's where we are in space, here's where we are in time. I'm sorry, I know I'm laboring this, but it's important. Now, print is a function. It's not merely something that we do atomically, it's got structure inside it. So what happens is, as we drill into that function, then we're climbing up the stack, we're finding other coordinates elsewhere in the program. This you understand. Your debuggers produce this all the time. You can see stack traces, you can see where you got to. But this was part of Dijkstra's idea of an execution coordinate. This is what you need. It's not just one number, it's this tuple of numbers which says not just where you are, but it tells you the history up to that point. It tells you how you got there. We don't care about the history along here, because the only way to get to line 13 is through the intermediate lines. But we do care how we got to this point, because we can get to that point through lots of different paths. So that the execution coordinate involves that whole tuple. Does that make sense? As I say, this is not anything new. This is not anything that you haven't already seen before. This is what all of your debuggers give you. There's one more step that I want to show you, which is possibly a little less familiar. And that's what happens when you create a loop. Now, Dijkstra said, for reasons, for computer sciencey mathematical reasons, which I will tell you if you want, but is not worth going into now, he said we should treat these loops as if they are function calls. So we're not going round and round the loop. What we're doing is we're entering and exiting and exiting and entering and exiting the loop, like this. So this is where we've entered the loop. Then we start drilling into the loop, and we can see we've created a stack to represent this, and we've kept a tally of how many times through the loop we are. Our debuggers don't do that generally. I wish they did. Because this, when you put all of those three things together, then you get a complete sense of where you are and how you got there. Okay? This is an execution coordinate. Now, what Dijkstra said was you can understand a program when every point in the program, that's every point in its textual description and every point in its execution, has a coherent execution coordinate. That's when you can understand it. And any program for which that is true is a structured program. So let's see what he was fighting against. This is, remember, 1968, when the Pascal was still a twinkle in Wiert's eye, and most people wrote in Fortran. And this was typical of the kind of code of the day. Can anybody tell me what that's doing? Anybody? Now, this is about the simplest example of unstructured code that I could come up with. But seriously, I have seen code worse than this. I've debugged code worse than this. I've inherited code worse than this. That they said, can you structuralize this into C#? No, I can't. Would it help if we animated it? Let's have a look. Well, what's going on here is we can see at each point what line we're on, and we can keep a track of what line we're on. But when we look at the time, well, line 14 could be this instant, or this instant, or this instant. And the history could be this history, or this history, or this history. We just don't know. So in this example of code, there isn't an execution coordinate. We can measure the line, but just knowing the line number doesn't give us the execution coordinate because it doesn't localize the time. Does that make sense? Okay. Now, this is not hard to understand. I'm saying things which should not be challenging you. I mean, you know you would never write code like this. You know, if you've even seen code like this, you know it's been consigned to history's dustbin. And quite right too, because this is awful. But if we were still writing code like that, I'm sure you'd agree it would be riddled with bugs. We'd never be able to control it. Well, what if I told you we still are? Let's just do a review of where we got to so far. The execution coordinate is this tuple. It's a sequence of numbers representing a stack. Each represents a specific location in the code, optionally with an iteration index. Okay, so that's what an execution coordinate is. That execution coordinate shows us, if it's structured, where we are in the code, where we are in time, and the entire history leading up to this point, which means if you've got that number, you can roll back. Wouldn't that be great if our debuggers did that? Incidentally, if it's not structured code, we lose these two. Finally, just because you've got a goto in the code doesn't mean that you're violating structure. The mathematical foundation here is saying if you want the code to be structured, if you want an execution coordinate, then you have to have this relationship between the time and the location. But that's all you need. So we have gotos in our modern code. We call them things like return and continue and break. What these are doing is precisely coming out of the flow of the code and jumping somewhere else. But they're doing it in such a way as not to violate this execution coordinate. Even assembly, you take a chunk of code, you compile it down to the binary, then, well, the binary might be, I mean, there's no concept of a loop in binary. It's all done with loops and branches, jumps and branches. And yet, it doesn't undermine the structuredness of it because you can still pass it through a debugger and you can connect it back to the original code and see where you are in the original code. You haven't broken the structure just by putting gotos in it. What we have done, though, is we've controlled our programs by producing limited versions of these gotos. We've tamed the gotos. Rather than allowing them free rein, we've tamed them. Okay, so that's the history. Now, these days, we write code more like this. And in this code, anybody not sure what this is doing? Anybody is sure what this is doing? It's typical of the kind of code that we write. But there's a problem with this. This is not structured, not in the mathematical terms that he has asked for. The reason is that when we execute this code, we step into this block, and then we execute some of the lines, and then when we step into the block again, we execute a different sequence of lines, which is not a problem, because if we know that we're here, and we know that we're in this block, then we know a lot about how we got there. But the problem with this is that which branch we're on, these are linked together because they've got this shared condition. So if we find ourselves on line 17, then we know we must have passed through line 12. This picture shows us this. And similarly, if we're on line 19, we must have passed through line 14. And the picture showed us that. But it means that when we actually try and look at this in these execution coordinate terms, we can't tell what the history is. From here, it could have been either of these histories. But we've lost our sense of this clear, unequivocal history. Exactly as what happened when I showed you that Fortran code. Now this, I said I'd tell you what the pattern is, what the anti-pattern is. This is it. The same condition repeated in more than one part of the code. Because the problem is that there's nothing obvious connecting those conditions together. I mean, when they're very close together, you can spot them. When they're very close together, it doesn't really matter because things can get it wrong. And you can spot it right away and put it right. But if they don't look the same, if these are not even in the same class or they're not even in the same machine, then you haven't got that relationship. And frequently, what happens is when these things get separated, they stop being synchronized. So look, what a goto does, normally you look at a series of lines and the lines go one after another, and if they're adjacent in space, then they're going to be adjacent in time. But what goto does, it says, no, these are no longer adjacent in space. We've got these two things which are separated, which actually are adjacent. It's like a wormhole in your code, right? They call it spaghetti code because it's joining these two things together. But what this is wormhole code. These two lines and these two lines are sort of in contact. They gear together like that, right? So these separate bits of code are in some kind of contact with each other, and yet they're separated in the code. They're separated, could be separated in the assemblies. Does that make sense? Now let's suppose these were separated, and let's suppose you're going to come along and make a fix. You're going to change some function of this. Let's suppose instead of having overdrawn an in credit, you want a special code for 0. That's where you're going to go and fix it. And how do you know to go and fix it there? And the answer is, you don't. And chances are, you won't. And that is where the bugs come from. That 90% of bugs that were all caused by that one anti-pattern, this here is that anti-pattern. It's having that one condition expressed twice and controlling 2 separate bits of code. Does that make sense? Any questions? Anybody? Okay. Now, can we fix it like this? Now, what we've done here is we've taken that condition out and we've put it in one place so that we're separating out the things that we're separating into 2 separate paths. Now, this is structured. This is fine, except for the fact that we've got this repetition. Tell me, who thinks that copy and paste is a good way to fix bugs? Didn't think so. Okay, so this isn't the answer either. I mean, we can take this and we can refactor it into this, and in some ways it's better, in some ways it's worse, but this isn't actually the answer that we're looking for. Incidentally, that should have been better. How long have you been looking at this code? That's what it should have been. That was incorrect. I've spent the last, 7 minutes with that code on the screen, and you all missed that bug. I rest my case. Okay. Now, let's go back over what we've just seen. This is go-tos. This is not coming out on my show very well. There's something gone wrong with the show. Go-tos destroy temporal identity. We've seen that because you don't know, where you are, but you don't know when you are. And they also destroy the history. Over here, this should be ifs. Yes, what ifs do is they conflate the temporal identity. I'm really sorry, I don't know why this is misbehaving. What go-tos do is they create flow spaghetti. What ifs do is they create these flow wormholes. And it's not just if, it's these synchronized ifs. They create these wormholes. Okay. I'm really sorry about this. I don't know why this is misbehaving so badly. New computer, it's an Apple. It should work. Why isn't it working? Okay. In order to create structured code using go-tos, then what we do is we have to not explicate go-to. We can't say go-to. We can't spell it like this. What we have to do is we have to imply the go-tos from the shape of the code, right? And that was the solution to the go-to problem. So how are we going to solve the if problem? Well, the answer is we have to imply the decisions from the shape of the code. And what we're going to do is we're going to talk about how we're going to do that. Incidentally, there is something that I want to point out here. This, where you can't see it, says go to. This, where you can't see it, says if and if. But look at this. Go to, in and of itself, doesn't destroy structure. Go to does one of 2 things. It either permutes the order of the lines you're executing, but doesn't necessarily destroy the temporal identity. It might scramble it a bit, but it doesn't destroy it. Or it creates a loop, and we know how to handle a loop. So go-to in itself isn't the bad guy. The problem comes about when you have a go-to connected to an if. Because then, sometimes you branch and sometimes you don't. I reckon that the wrong person, I reckon the wrong guy has had the blame all this time. I don't think that it's go-to that's evil. I don't think that it's go-to that's harmful. I think it's if go-to that's harmful. And between if go-to and if, do you see a common pattern here? So, ifs are the problem. Okay. Now, I promised you right at the beginning. I said 90% of bugs come from this pattern. have I convinced you? Is anybody not convinced that that's true? Thinking about your own code that you work with, thinking about the bugs that you encounter, is anybody not convinced that that's true? That's pretty good. Okay, that's like no hands went up. So now I'm going to convince you of the other half of it. How many of you do debugging? In fact, how many of you don't do debugging ever? Right, so all of you are going to know what I'm going to say here. What do? You understand what the conditions are that create the malfunction. You run the code, and you step through it until you find the malfunction happen. And then what do? You go, oh, look, we've got a null pointer here. So you put in a little condition to test for that special case, patch it up right there, and then move away again. What have you done? You've just put in an if. Because what you've got is some condition somewhere in the code that has created that pathological condition. Is that me? No. That would have been so embarrassing. For me, it's really embarrassing for him now. Yeah, so what you've got is you've got this state, you've got this condition somewhere in your code which is creating this pathological state. And then somewhere else, you've now got a new condition to test for that state and patch it up again, which is precisely the synchronized ifs which leads to bugs. Because next time you come around, and this bug here, or this pathological state, is affecting somewhere else, now you've got to fix it over there. And what happens when you come to maintain it? So now you've got these little conditions, these little tests spreading out all over your code, all connected with the bug fixes, all where you think you're making your program more reliable, every one of them introducing new defects. Incidentally, you know the difference between a malfunction and a defect? Okay. If you're driving down the road in your car, okay, nothing's wrong, the car's working, and then suddenly, okay, what's happened is something is now wrong with the car. The torsion bar's broken, or the tire's gone flat, or the linkage is broken, or something like that. But there's now a defect in your car which is causing the malfunction. So you go in, and you correct the defect, you pump up the tire, or you mend whatever's broken, and now you can drive away again. Point is, you've got these two things. You've got the malfunction, which is how you know there's something wrong, and then there's the something wrong which needs fixing, and that's the defect. Now, in software, things don't break. In software, things go wrong because you put things in them that go wrong, right? But how do you know there's anything wrong with them? Well, the answer is there's a malfunction. You try and do something with a program, you expect it to behave in a certain manner, it doesn't behave in that manner, so now you've got a malfunction. So now you trace back, and you see if you can find the defect which caused the malfunction. And then you fix the defect, and hopefully the malfunction goes away. In fact, you get two new ones. It's like a rat splat, isn't it? But you need the defect to create the malfunction. Every malfunction is associated with the defect, and the defect plus the malfunction is what we call a bug. But not every defect creates a malfunction. Quite a lot of defects sit in the code for years where you can't see them, they don't do anything, they're not triggered in just the right way to cause the malfunction, so they're just sitting there waiting for you. And these multiple ifs, those are precisely defects. They're not malfunctions, they're malfunctions in waiting. They're trolls under the bridge. Okay? So what we're trying to do here is we're trying to reduce the number of defects. So again, to go back to the promise, I said 99% of our secondary bugs were all caused by this one anti-pattern. It was our bug-fixing efforts that were causing our code rot, that was causing our technical debt. Does anybody not believe that? Does anybody not believe that of their own code base? Have I delivered my promise? Go on, say yes, Jules, somebody. Thank you. It is an apathetic affirmation. But I want to be really, I mean, this is not just me saying, oh, good, come on, beat me up. I want you to be clear about this. I know I'm claiming something big, and I want you to be sure that I'm as good as my word. So have I made my case? Is there anything that you want me to go over? Do you want to challenge me? Now's your opportunity. Okay, good. Good. We need to fix this. We need to fix this by more than just going back and patching over our bugs. We need even to do more than go back and find the original defect that causes our malfunction, rather than introducing a new defect. What we need to do is we need to find a new concept of decision structure in the same way that back in the 60s and 70s they were looking for a new concept of flow structure. This is what we're going to do today with the rest of today. This is what we need to do. We need to concentrate our conditions. We saw that the problem came about because we had two conditions testing fundamentally the same states in two different places. I'm going to talk a bit more about exactly the nature of that problem, but if we can take that understanding of states, if we can take that decision in just one location and then find the consequences of that separated. I mean, what we see now, sorry, let me find another way of expressing this. What we do now is when you say if and then what you're doing is you're saying here is the decision and here is the consequence, and they're both in the same place. So if we've got consequences in different places, then we have to replicate the condition. We have to replicate the test. But replicating the test is what causes the problem. So we need to find a way to separate the test from the consequences and concentrate the test in one place and then have the decisions all dependent on that test up there. Does that make sense? This is our new concept of flow control. And it's not as hard as it looks. So we need to concentrate our conditions. The decisions that are based on those conditions need to be implied by the shape of the code. We need some new mechanisms to represent the ifs. In the same way that we needed new mechanisms to represent goto, we need new mechanisms to represent if. Goto was replaceable, and this again was based on a mathematical theory. It was replaceable by function calls, by loops, and by a switch, by if and then. And that was all you needed, and you could build the whole of structured programming out of these three constructs. I think, similarly, there are three constructs that will replace if. And I'm going to explain to you what these are today. Well, now this is the other point. It's all very well to talk about this. Back in the 60s and 70s, they were inventing new languages like C and Pascal and Algol. But we haven't got that because we have to write code today. So we have to do this stuff in existing modern languages. We can't wait for the new languages to come along. Again, back in the 60s and 70s, they didn't wait for the new languages to come along. What they did was they developed new kinds of discipline and new kinds of programming hygiene. And they learned how to use these techniques before they made it into mainstream languages. So we're going to be doing the same thing. Right, let's talk about assert. What is this stupid computer doing? Okay. Got a bit of code here. You can tell what it's supposed to be doing, can't you? There's a problem in that. In fact, there are several problems in that. Anybody care to hazard a guess? So your complaint is that A might be negative. Okay? All right. So what would you expect to do about that? I would assert on it, yeah. Just like that. Now, I've expressed this in this way because I'm saying that I want to say that I'm making the statement, this is what I want, this is what I think is a valid call. And if it's not a valid call, then this is the consequence. So that's why I'm throwing the exception. I'm being explicit about the action that I'm taking here. And that's the point I want to make here. Anything else wrong with this? Are you happy with this now? Actually, I'm assuming A is numeric at all. But fair enough. So what do we do about that? Now, this is a slightly different kind of assertion. We should be able to tell at compile time. We might not be able to tell at compile time what the value of this thing is, but we should be able to tell at compile time what its type is. And if the type is wrong, then we don't want to throw an exception once it starts running. What we want to do is send a message back out through the compiler to produce a compiler fault. So what we're doing is we're sort of extending the concept of type right into the compiler itself. So the reason for showing this is that we actually have two different consequences. We've got different things to do when the assertion fails. Normally what an assertion does is it just produces an assertion failure exception. But I'm saying actually we want to do more, that assertions can be worth more than this. But it means that if we do this, particularly if we've got things like this, then it means that that takes a whole lot of testing out of the execution. It means it's the compiler looking for us. So it means that at the point at which we start running this code, we can be pretty sure that it's numeric. And if we can actually do that testing at compile time, then we can be pretty sure that it's within range as well. Don't know if any of you have handled languages that use contracts, things like Eiffel. Eiffel tries to push as much of the evaluation of the conditions into the compiler as it possibly can, so that when it starts executing, it doesn't need to test them anymore. So that is how you would express that in this language. You would say, you'd throw an error if you possibly can. Now, you might not be able to prove that, in which case you're falling back on that, but if you can find that, then that's how you'd find it. Assertions are really helpful because what they do is they give you a sort of a super type superimposed on the type system that you've already got. You can be explicit, it's part of documentation, excuse me, it's part of documentation as well as part of the reliability of your code. Here's an important point about this. Remember what if does. If changes the course of the program. It either goes that way or it goes that way. But we're not trying to change the course of the program. We're trying to stop it. An abort means an abort. So, where we're trying to synchronize these different conditions, there is no synchronization here. Because once one of them's fired, none of the other ones can because we have shut down the flow. That's the entire point of what we're trying to do here. We're trying to make the problem worse. Or we're trying to make the consequences worse, not better. Several different kinds of assertions. We can either return a null object or a default object. We can throw an exception. We can call die means to actually shut down the program. Has anybody ever done any embedded programming? Okay, right. What goes on in embedded programming is that you will have a process running on the chip. You'll have your normal program running, but alongside it you'll have a process which is just checking. Sometimes it's just a timer which you have to kick regularly. Sometimes it's a separate monitor process. But basically there's something there which is checking the health of the chip. And if that fails, and it goes, no, I don't trust this, then what it will do is it will shut everything down and try and restart it. So, you know, where your IT department says switch it off and switch it on again, you've now got a little program doing that. And some of them are more intrusive than others. Back in the early days of the Intercity 125, that was controlled by 3 chips sitting in a socket, each one running slightly different code produced by different programmers. And what they did, do you know about this? Okay. What they did was every now and then, every sort of half second, they would produce their results and they'd all compare the results. And there was a piece of hardware that was there comparing the results. And if one of them disagreed with the other two, there was a little explosive charge which blew the chip out of its socket and the train slowed down and continued on 2 chips. Fortunately, most of them are not quite that intrusive. But that's what die means. Die will mean not shut down your program and throw a crash and the plane dives out of the air. It does mean something's gone seriously wrong, so try and restart if you can. And then error is entirely compile time. Sometimes you can produce that, sometimes you can't, but if you can, it won't even compile. So that's assert. This is one of the things that we're going to use to control our conditions. It's still a condition. It's still fundamentally an if, but its purpose is now shutting down the program or even stopping it from starting. It's not to change its flow. Any questions at that point?
Doesn't return null or default change the flow?
No. The point about returning null or default is that that's supposed to hand back something which the rest of the program can carry on with. In fact, we're going to be talking about that in a minute. What that actually means. But yes, that's something that the program should be able to carry on with.
Not a question, but just a comment. If it's mission critical code,
yes.
then as you blow up, you've got to maybe assert, log it, and then do something with it still.
Absolutely, yes. And so understanding what that assertion means and understanding what the consequences mean, yes, you're going to need some kind of downstream support. So if you've triggered an assert, something's going to happen. And yes, you're right, you do need to log it. Of course you do. All right. Doing this in existing languages it's pretty easy. We can do pretty much all of them with exceptions. The nice thing about an exception is that an exception doesn't return. And you can use the exception constructor to produce the log. Obviously, the error needs compiler support. How many people like writing compilers? I do. If you do, then actually patching things in around the outside of the compiler, particularly now we've got Roslyn, makes it really easy. If there are things that you can look for, features in the code, then you can just link them into the compiler, write them in, and now you've got some custom compilers running. And you'd be surprised how easy it is. Honestly, just give it a go. Okay. Let's talk about values. There is something very wrong with this program. Now, here is a factorial program written in a modern language. It's a fairly trivial thing. It's a recursive function. Anybody not understand how this works? Now, the reason for showing you this is because there is something in every modern language, there's a concept of polymorphism, which means that we don't necessarily need to take the factorial of a number. We can also take the factorial of a string. And this is perfectly legal in pretty much every language that exists. And this causes you absolutely no difficulty whatever. What we're trying to do, remember, is to get rid of this condition. There are languages, like Haskell, like F#, mostly functional languages, or pattern matching languages, or transformation languages, that polymorph not merely on the type, but also on the value. So this is what this would like in rather cod Haskell. I mean, I'm not going to show you the worst of Haskell, but this is how Haskell would express the same thing. So it would create a function which takes a 1 as an argument. It would create another function which takes any number as an argument, and then it would create another function which takes a string as an argument. So what you can see is that this is polymorphing on the values as well as on the types. Now, this is important because what it does is you know what the value of polymorphism is. You don't need me to tell you that because you use it all the time anyway. But what this does is it takes this out and leverages it another level. This looks like conditions, but it has to be expressed at the very highest level. It has to be expressed at the level of the function prototypes themselves. Now, the consequence of that is that if we're going to follow that pattern, then it means in a conventional language, we have to make it look like this. Basically, when the function starts, the very first thing you do is a test. And it should be a switch. And it should be a switch with a default case at the bottom. So actually, this should be expressed as a switch, case 1 and case default. But other than that, you can express that pattern using conventional languages. And because it's happening at the very highest level, and because it's a switch, there is no possibility of any kind of synchronization. Does that make sense? Okay, again, these are very simple things to do. So, oh, come on. So this is what this would look like using that same, using that pattern that I just showed you. This is the code that we saw before, which had the problem in it. This is what it looks like in this pattern. This is just a tester to get it started. But what we're doing here is we're putting together, we're folding these up together like so, based on polymorphing the value. Does that make sense? And it means that we can just keep on adding cases, as many as we want, across as many values, across as many types as we want. And this again, this would express actually using switches. Any questions at that point? So, all right. So here's the recommendation. You do the condition before anything else. You do it with switches rather than with ifs. You can alternatively use ordinary polymorphism. You can create specialist classes. I mean, here we've got an example of plus money. Remember we had the money examples before. So here we're saying, well, actually create a special plus money class which will only construct if it's a positive number. Or use a language which is designed for the job, like Haskell or F#, because they will actually help you quite a lot. F#, incidentally, does this naturally and couples to C#. Simply, you don't even have to think about it. Was anybody in my F# class yesterday? Okay. Right. Now we're going to come to something which is a little bit more involved. There is a bug in this code. Not exactly a bug, there's a defect. This is an example of the kind of synchronized special casing that I was talking about before, where it's disguised. You can see what we've got here. It's a perfectly simple class with some functions inside it, containing within it something else. And we have to set that to null. If we don't set it to null, then if we leave that blank, then this will set it to null for us. This is behavior which you know about. But it means that every single time we ever use that, we have to test. Because little class is promising some interface, and we can assign anything into C which will honor the little class interface, except for null, which we can assign to C which has no interface at all. This is a null pointer. The guy who invented the null pointer, sorry? It was Tony Hoare. He put it into Algol 68. I don't know why I'm looking at you. He put it into Algol 68 because he thought that it was simple and it was trivial and it wouldn't do very much harm. He now admits that this is responsible for more bugs than any other single cause. He calls it his billion-dollar mistake, and he is very ashamed. So the guy who invented this doesn't believe in it, so neither should you. The problem is that what this means, particularly if we leave that blank, is something very odd. There's no real reason why this should even make sense. If we write this down, then what it's going to do is it's going to try and cast 4 into a little class in any way that it can. But what that means is not that it's going to cast a null into a little class, it's going to just assign the null to C, and it shouldn't. If there was any logic in the world, it would mean that. So, and if it meant that, we'd never have to mess about with all of those tests, because whatever was in C would always have the little class interface. So what I'm going to suggest here is that you should never, ever use or allow anywhere near your program a null pointer, because the null pointer is precisely a source of bugs. We know it's a source of bugs, and we even know what the pattern of the source of bugs is. So always, always create null objects instead of null pointers. And a null object can be as trivial as you want it to be. And in fact, I've got another talk where I explain what the theory behind these null objects would be. But the fundamental thing is that they should be only enough to allow the rest of the program to work. So things like dev null is an ideal example of a null object. It has all of the interface that a file does, or that a stream does. It just eats everything, or it produces an end of stream right at the beginning. So you can treat it as a file, you can treat it as a stream, but it's not a stream. It's a null, okay? So, null objects expose the interface. Null pointers don't have any interface at all. Null objects, they can just be used naively like any other objects, but null pointers need to be guarded on every single use, which is exactly the anti-pattern I'm telling you about. The null objects can be checked entirely at compile time, which is when we should be doing our checking. These cannot be checked at compile time. They have to be checked at runtime. We shouldn't be doing checking then. So there is absolutely no reason to be using null objects, null pointers. There's every reason to be using null objects. There's no reason to be using null pointers. I think I had too much pudding at lunchtime. Okay, so what I'm hoping this is going to be is, yeah, if we interpret that to mean that cast, then it means that these simply go away. And that is a much simpler program to understand. Any questions at that point? Right. Now, this is actually the thin end of the wedge. We can do a lot better than that. Okay. We're all using object-based languages now. Is anybody not using object languages? Okay. Every now and then somebody puts a hand up and says, no, I'm still in Fortran. I actually had one guy still in COBOL once. I didn't know there was anybody still writing in COBOL. Yes. They just don't seem to come to these conferences. Okay. Right. Every time you invoke a method on an object, there is an implied condition. And that condition is that the thing that you're invoking the method on is a member of is an instance of the class in which it's installed. Okay? Now, remember what I said to you right at the beginning. We have these consequences based on our decisions, and we have the decisions and we want to separate them. So look, the consequences of a decision are all contained within a class. The decision itself is the factory that creates the class. We already have the mechanism to achieve this separation that we want. It's the object system itself. It's just that we're not using it for that. So, let's take an example of a class which we're going to be using, say in the previous example, in the bigger class. We can have a number of different subclasses which will all implement whatever interface that is, all constructed in different ways, right? This you're used to, this you understand, okay? But what this means is that depending, and what we've done is here is we've polymorphed again on the type of the thing that we're constructing against. But obviously, you can polymorph on anything that you want. But each of these produces a different class. Each of these produces a different object, and each object is exposing whatever interface is defined in there, and it can attach its own, it can override anything, any method that it wants. So this is where you're representing these consequences. So we can get up to here, and we can say, in one place, this is the thing that we want, and then hand it back from here. Now, this is a notation which I use a lot in when I'm sketching, and I've actually written pre-compilers which expose this inside a language itself, so I can represent this as real code. What this is saying is that if we attempt to construct one of these using an integer, then what it will do is it'll actually construct one of those and then hand it back as if it's one of these. So what this is doing is it's automatically downcasting. So what we have here is we have a factory. Basically, this is representing the factory, but it's also upcasting. It's inside the little class itself. Does that make sense? That what we're saying is we want to construct one of these little classes, and if we construct it with a null, then we're going to hand back an object which actually has all of this null semantics embedded in it, but the owner doesn't need to know, because the owner is just treating it as if it's one of these. This you can do today. This concentrates the entire condition at this point. Remember before when we were talking about the value polymorphism, I was saying you do it with a switch. Here is a switch, but it's operating over a much larger scale. I said we want to concentrate together all of the consequences of each decision, but here is precisely that concentration. They're there. they're named so that you can see them clearly, and they're grouped together so you can see how they relate to each other. You're never going to get them, one of them going out of sync with another, because you can see the whole class all at once. And when the user of little class is starting to use the consequences of those decisions, how does it know which one it's using? It doesn't. It shouldn't, because that is where the decision should be taken, not in the client and not over here. This pattern completely gets rid of that bug-making anti-pattern which I showed you at the beginning. Yeah?
It's important that I know that I have a null. I mean, if I try to instantiate my flight control module and it hands you back the null flight control module and I say launch plane, I'll die. So it's important that I know that I got a null back in that case.
Yes, it is. But in that situation, assuming that we don't have that, assuming everything needs to be instantiated and everything needs to be properly constructed, if you don't want a null flight control system, then just don't provide one.
If I still have the possibility that the flight control system is not constructed for me at runtime, then I have to make the check that you're telling me I shouldn't be making on a null pointer.
What's the possibility that it won't be constructed at runtime?
That a resource is not enough memory. I mean, I can invent a lot of reasons why I can't create an object.
And if you can't create an object, then you should throw an exception. It's a different argument, but I think the only valid use for an exception is a failed constructor. But if you want the object and you ask for it and it can't hand it to you, then that needs remediation. And again, in real-time systems, what you tend to do is everything gets constructed, all of your memory gets assigned right at the very beginning, and then once you're flying, you don't even match the heap. It's just you use the memory as if it's static. Okay, you happy with that answer?
Yeah, the exceptions are a reasonable approach.
Okay.
How would you implement this in C#? Well, you're fighting against the compiler. Stuff like that.
Yes, you are. I think that's what the next slide is. Almost. We're coming to that. But what you do is you create a factory object. A factory method. Okay. So what we've got going on here is we're defining the interface in here, and it's the base class for all of those, and it's the factory for those, and it's all in one place. And what people sometimes ask me is, why put it all in one place? Well, why would you want to separate them? It makes more sense to put them all in one place because you've got all of your decisions concentrated together. It's one point where everything is focused. So, what does that look like using that notation for here? Okay. So we're doing the same thing that we did before. What we're defining is this money class, because the money class is where we're concentrating the decision. Here are the two different subclasses, the plus money and the minus money. And then here is the constructor. And so again, what we've done is all of those separate things, which were spread out over those two ifs, they're now concentrated into one decision, and you can see what the consequences are, and you can see what the decision is, and then you can see what the consequences are here. And I think, even though it's spread out a bit on the screen a bit more, I think that's actually a much clearer exposition of what was going on than the previous iffy-butty thing. Particularly when you start scaling this up, and it scales up very neatly. So, this is the question that you're asking. You use static factory methods. There's a problem when you're using static factory methods because they don't look like constructors. So what I've learned to do is, if I can't do any better, then only ever use static factory methods and make all of the constructors private. And that way you never get caught out. So it looks a bit different, and the very first time you address the code, it's a bit surprising, but that's fundamentally the pattern. All your constructors are private, use factories for everything. In fact, in C#, it's the only way to downcast like that, because when you do C#, every time you call a constructor, that's what it gives you, and it's not like in C++ where you can downcast. You're stuck with it. You can expose the subclasses directly. We saw examples of doing that earlier on in some of the previous examples, but you can actually just create the class, the subclass of whatever you want if you know what you're doing. So you can actually bypass the factories if you're careful. It's not so good, but... And then finally, pre-compiling. I said that pointer notation, that switch notation, it's very easy to compile into your code. When you're doing that, I mean, Roslyn exposes them, or you can pre-compile it fairly easily. There's all sorts of things that will help you do pre-compilers. But when you're doing that, you can use the pre-compiler to make sure that every single thing, every field is properly initialized, and nothing is left to just sitting around being null. Yeah, and you can make sure that every time you give it a function, it's explicitly cast. So the pre-compilers, they're not very hard, but they do give you a huge amount of reliability and of robustness at that level. So the pre-compilers, they protect you from your own, from incorrectly setting up the fields. And it also allows you to create these switches. And it's not hard, and like I say, Roslyn's available, and there are pre-compiler languages available as well, just transformation languages, which make it fairly easy. Okay, so let's summarize. We know, and I don't need to persuade anybody, that GoTo is harmful. But actually, the wrong guy got the blame. It was always if. The only reason why Dijkstra, who is a very great man, well, was a very great man, didn't say this was because he didn't have an alternative. He had an alternative to go to. He constructed structured programming, but we were nowhere near objects in his day. So he simply didn't have a recommendation to make. But the logic, his reasoning behind this applies equally to if. Okay, GoTo causes spaghetti code, which is unreliable. Spaghetti code means it puts two bits of code adjacent in time. What ifs do is they create wormhole code. Wormhole code is this spooky action at a distance. Now, I'm trying really hard. Everybody knows what spaghetti code is. I'm trying really hard to get this meme out into the world. Tell everybody about wormhole code. Because once you see spaghetti code, you can't unsee it. Once you start seeing wormholes, you can't unsee them. Next point. The antidote to GoTo was flow structure. We knew this back in the 60s and 70s, and it's now absolutely routine. It's unthinkable to do it any other way. The antidote to the if problems is decision structure. We haven't got the languages to do decision structure now like we've got structured programming languages, flow structured languages, but we will do. I'm absolutely convinced that in 10 years' time, we will have languages which have this kind of thing built into them. But for now, oh, come on. Okay. Structured languages work because they replace GoTo with flow structured constructs, the fors and whiles and throws and all of those sorts of things. Throw is a more recent addition. But a decision structured language, it needs rather more complex things. I mean, these are actually reserved words, but you've seen that in order for a decision structured language to make sense, then it's not words, it's shape that makes the difference. And so we've got things like assert, but value polymorphism, it's in the language itself, it's not a keyword. And these downcasts that I showed you, that also is in the language itself. We can fake them for now, but they're not simple keywords like these are. But fundamentally, it's the same attitude that if we can take the problem and we can obviate the problem by replacing the keywords with the shape of the code itself. Okay. You can do structured programming with GoTos if you know what you're doing. You can do structured programming with if, you can do decision structured programming with ifs. You've just got to be careful while we're waiting for the language technology to catch up. So, I'm just winding up now. This is the thing that I asked you about halfway through. Misusing if is responsible for more bugs than everything else. We misuse it when we write our program. We grotesquely misuse it when we debug our programs. It's really hard when you're debugging a program to go back to the defect. We don't even bother to find defects. We introduce new defects. But That's the wrong thing to do. We've got to find some way, not even of fixing the defects, but of not putting the defects in the first place. Those patterns, those anti-patterns, they are everywhere. In fact, they're so frequent that we barely even see them. I'm amazed it's taken 50 years to spot this. It's not like objects haven't been around for 50 years. It's not even like this pathology hasn't been around for 50 years. We have known about go-tos and why they're so pathological for 50 years. I truly don't understand why it's taken so long to catch up, but it has. We need the decision-structured language constructs, but in the meantime, the only way to fix this is good programming hygiene. So, good code reviews, look for them everywhere. Just, set up your code editor to make if flash red or something, because without the ifs, you have to be judicious about it, but without the ifs, you don't have the problem. And to finish, if you're in any doubt as to the value of this stuff, I mean, I know that I've been throwing a lot at you, but if you're in any doubt as to the value of this stuff, this picture should explain to you the reason why. 90% of the primary bugs come from the one anti-pattern. Virtually 100% of the secondary bugs come from this anti-pattern, and this here is a picture of your code rot. Any questions? Yes.
So I just have a question about your the factory method and having private constructors.
Yeah.
Are you not sort of hard baking that into your class then, sort of restricting any further? So if you come up with a new class to add into that factory pattern later on, you sort of pre-bake that and then you will retest all of that. It doesn't feel like an abstract solution. It's not an abstract factory method. It's baked into your class.
Okay. Let me concretize the question to make sure I've got this right.
Sure.
The example I was giving was printing out the money. So it selected a color and printed out either CR or DR. You're saying, let's suppose we introduce the account's null. So we need to print it out as nil in black. Or let's suppose the account has got dollars in it.
Over 10 grand or something.
Yes, okay. And what you're saying is that we've baked into the code the fact that this is there. Now, if we're doing this conventionally, then we would have to find in the code every single place where anybody referred to a depiction of money, and we'd have to select which kind of money it was, and we'd have to find the correct depiction. And that would involve a change in the code. Doing it this way, we'd have to create a subclass representing this new type of money, and then we'd have to reference that subclass in that factory constructor thingy. And it's still a matter of changing the code. You still have to reach into the code because beforehand you didn't know about this over 10 grand or you didn't know about this null. What is the problem with having to change the code because the requirements have changed? Have I understood your question correctly?
I think so, yeah.
So why the question?
So I thought the conventional wisdom of using a factory method was that it was an abstract factory method and therefore you could substitute in a different one rather than...
But the factory still needs to be able to take its decision on some basis. Now, we don't know what the bases are. You just introduced one. I gave you one, it's 0. You gave me another, it's over 10 grand.
So my example, perhaps I'll introduce a new factory method that says, okay, if this condition's met, then create this new class. If not, I'll just call the old factory method.
No, I would say put it all into the switch. Because you have this one switch which says, okay, we want to create one of these things, and we want to create some subtype of it because we've got a bunch of consequences based on which one it is. So here is the point at which we take this decision. Now, if it's over 10 grand, then we know it's positive. So that should come first in that switch, or in fact, it should be more specific in polymorphic terms. So it should be the more specific example in the switch. So that should overrule the fact that it's positive. And in practice, you do that by listing it first if it was a switch statement.
I suppose my point is that if that piece of code is written, tested, passed thing, do I then want to go back and fiddle with that, change that, or do I want to sort of build on that in some other place? That's the sort of trade-off.
I see. No, I would say place it right there. because otherwise what you're doing is, again, you're spreading out the consequences. Because over here, you've got, is it positive? And over here, you've got, is it greater than 10 grand? And actually, they seem to be part of the same choice. So where they're genuinely orthogonal decisions, they should be separate. But where they're genuinely overlapping, I think they should be together. Are you comfortable with that answer?
Yeah.
Okay, cool.
Going on from that, isn't that sort of violating the open-close principle? Because you're always having to change, you can't just extend something once it's written. You have to go back and change it.
Again, I would ask you what you would do in a conventional circumstance. We are open in as much as we can create as many new subclasses as we want to represent this more and more specialized behavior. But if you have a factory, then the factory needs some basis for taking its decision. And if you've introduced a new basis, then where do you address that? I mean, do you put that in a subclass? I think that's the wrong place to put it. I think that, you know, you have a piece of a function there. You have a locus, which is precisely there to take your decisions. I actually don't see any problem with going in and touching that. Now,
The problem is that you don't always have access to that code. It's a third-party library that's exposed some abstract interface that I want in subclass. If I can't change the factory method, I have to make my own factory method perhaps that calls into theirs and find all the places I use that factory to replace them all. And I don't know if that's a good or bad thing because the points you make are very good, but it does kind of clash with a lot of what we've been taught as O developers for the past 4 years about open, close, and extensibility, or it seems to.
yes.
I suppose the point is you need one place that you know is your decision-making point, and if you have a third-party library, that you have to sort of take over control of that.
Yes, I think that's true, and I think that if you're working with a third-party library to which you don't have access, and it is taking its decisions, then in a conventional world, you wouldn't have access to its decisions either. And it may be taking decisions which it's absolutely reliant upon, and it doesn't want you tampering with that. So I would say that if you've got something which is closed, where the factory is inaccessible and you can't get it to change it, then actually you have no business in there trying to fiddle with it. You shouldn't even be trying to override that.
I guess.
And in fact, let me amplify that. Let me amplify that. The example that I showed you showed the subclasses actually defined inside, in the scope of the parent class, where they weren't even accessible outside. It was, you know, the client couldn't even tell what the class of the thing being handed to it was. So in that sense, that whole structure was closed. If you don't have access to it, closed is how it remains and closed is how it should be. Because otherwise, you're tampering with the innards of somebody else, just pretending that you're not.
That's fair enough, but I mean, there's plenty of libraries I can get in C++ that I know that give you an interface and they say, extend this interface and we'll still work with whatever subclasses you make.
Yeah.
They don't provide factory functions, they just say instantiate what you need. And the advice you're getting seems to be, you shouldn't be directly instantiating it with using factories. So the natural question becomes, how do I write a factory for a library like that wants to be extensible and open, but also wants to follow your rules, which seem quite reasonable? Is there some kind of extendable factory pattern that you run into or something like that that addresses these problems?
You see, I think I would do that inside the compiler. I would say that. I think what you're asking me is, well, here is how people do it, and here is how I'm doing it, and how do we do both at the same time? That's what it fundamentally boils down to. Now, ultimately, I would say choose. I understand about these libraries which are extensible and you create your subclass, and I have absolutely no problem with creating those subclasses. That's a jolly good way of extending a piece of functionality. But the problem that we've got is not to extend the functionality. The problem that we've got is to extend the functionality in a non-linear manner. We were trying to take decisions, potentially quite far-reaching decisions, in the course of that extension. So if you've got just one library or just one class which you're then trying to extend, fair enough. But if you've got a whole constellation of classes and they've all got to work together, and you've made an extension down here and you're trying to hand it onto there, then there's very, very tight restrictions on what you can actually do with this new class of yours if you're handing it in. There are a whole bunch of other principles, like Liskov, for instance, which limit what you can do. And these things are not gifts from God. These things are conventions to help us work with those sorts of architectures. Things like C# require you to follow Liskov. You can't ever hide anything, but things like C++ don't. And so C++ has got different kinds of inheritance, and you can play different games. And so those sorts of uses of libraries, you have to be much more disciplined if you're doing them in a language like C++. So what you've got there is two different approaches to how these libraries interact with their environment. I admit I'm proposing a third. And I'm not even saying that this is better than the idea of extending a pre-existing class. But what I'm saying is that if what you want to do is extend a pre-existing class by multiplying its subclasses, by multiplying its downcasting, then you have to do that with the acquiescence of the class itself. Because otherwise, it's just going to lead you down into trouble. Because if you're giving the class a piece of functionality which it's not expecting and which it's not prepared for, or if you're giving the client a piece of functionality which it's not prepared for, which you can do with those subclasses, then things can break all over the place. So I do think you do it this way or you do it the other way. Once you're into this factory method thing, then you're stuck with it. And so in the case where it's already closed and you can't get to it and it's a third-party library, do what they want you to do. Don't fight them. Are you happy with those answers? You're not, are you?
It's a tough question.
Aye, it's a tough question.
I think what you're proving is it needs to be a language feature rather than something you implement in an existing language.
I do very much believe that. I think that we can only go so far with the programming hygiene that we've got, and we can only go so far with the legacy that we've got. I think that when we start getting into more fundamental language support for these things, and I'm absolutely convinced that we will, then I think that a lot of these questions are going to go away because they're going to be right there in the language. Yeah.
I'm slightly, I kind of get what you're saying, but I'm kind of like thinking of cases where you write a class where you have kind of members on that class that represent some kind of state, and on construction it might be in one state, and then you do things to it and it goes into another state.
Mm-hmm.
And you want, and those conditions are not, the kind of conditions you're talking about appear to be conditions that are always going to be true for the whole lifetime of the object. But I can see that if you wanted to eliminate conditions that change over time, then you would effectively have to kind of discard objects and create new ones that are in this new state. Do that, but to my mind, that sounds like it could actually be a very painful way to write code for certain types of applications, certain types of algorithm.
Yes.
You know, I don't know, you write a string plus and you want to do something when its content becomes empty. You know,
Yes.
rather than kind of having a separate one for an empty list and somehow switch between something that's got something in it to something that hasn't got something in it.
Okay. There are several different answers to what you're asking. It's a fair question. The first thing is, we are not trying to eliminate ifs. Of course, you need to take choices. What we're trying to do is eliminate synchronized ifs. More to the point, we're trying to eliminate synchronized states. So let me give you an example of what I mean by that. We've got a system which we want optionally to produce logging output. So as it starts up, it looks into its configuration and it finds possibly a file, the name of a file that we want to log to. And if there's no file there, then we don't want to log it. And if there is a file there, then we open the stream to it. And then at some other point, we start constructing a message to send to that stream. And then at some other point, we say, okay, we've finished constructing the message, now send it out. Now, at the point at which we send it out, what are we looking at? Are we looking at the configuration? Are we looking at the existence of the stream? Are we looking at the existence of the message? Which one of these is indicative of the thing, of the task, of the decision that we're trying to take here? Well, the answer is none of them. The answer is that decision has already been taken by the thing that we're sending the logging to, right? So those decisions that you can take ahead of time, those are the things that you're taking. The things that, when you've got lots and lots of decisions consequent on that, that should be behind that class boundary. That's what that's for. Individual conditions, I mean, you know, we have to take a decision at some point, are we going to log or not? So it's perfectly okay to have those in the program. The second thing is that actually you can create short-lived objects representing these decisions or representing these collections of state. We're not talking about having things hanging around for a long time. You can create things and destroy them and create them and destroy them. Again, in C++, you do it on the stack. It's part of building a stack and tearing it down. I know that managed languages, they have to churn through the heap, but even then, you can create short-lived objects. That's the main answers. Are you comfortable with that? Okay. But we're not trying to replace every if. We're trying to replace the synchronization. Yeah.
What's the difference between the synchronized if and the synchronized switch?
Nothing. You can be done with both words.
So no, it's just sort of imply that we should be using the switch.
No, the point about the switch is that it clearly telegraphs what you're doing. A switch, it happens at the very first point of the procedure, and it happens. If you find yourself writing the same switch in several different procedures, then at one level you've got a degree of security that you haven't got using ifs, because at least every if should match, every switch should match. But if it takes longer to write a switch. It seems to take up more space on the page. So if you're starting to play silly buggers, then you know you're playing silly buggers, and it's up to you.
So, but I mean, the whole point is that you could have synchronized switches throughout your system.
You could.
You wouldn't necessarily know.
But you would spot them, because ifs, they're just peppered right the way through the code. If, again, to go back to the bug fixing case, let's suppose you've found the malfunction and you've found the state which is triggering the malfunction. What are you going to do? Are you going to put an if in, or are you going to put a bloody great switch in there? You're not going to put the switch in because they're heavy and they look heavy. It's much easier to put the if in. Okay, any more? Yeah.
Do you see any scope for refactoring tools or code analysis tools to sort of help with sort of identifying these strings to help us sort of compile support?
I have to admit, I haven't explored that. What we found in that big code base that we were having the problems with was that it was a mess. It was a serious mess. A lot of it had been translated first from Fortran into Delphi, and then from Delphi into Delphi.net, and then from Delphi.net into C#.net, and then bits of it started to move back again, and we were getting chunks of C in Polish. I mean, it was just a nightmare, this code. And we were trying to find out ways in which we could refactor it. It wasn't worth the candle. In the end, what we did was we said, okay, well, when we start rewriting bits of it, when we were writing the new code, we tried to write it clean. And when we had opportunities to take out the old code and replace it, then we would rewrite it from scratch. A lot of the time, I mean, we had no unit test or anything, so we didn't even know what it was supposed to be doing. So we'd take a guess at what it was supposed to be doing and rewrite. So we actually found it easier to rewrite and to re-engineer than we did to try and refactor. Other than that, I have nothing to offer. Okay, any more? Yeah, okay. Keep them coming, man.
Functional programming,
Yeah.
I suppose some people would say rather use functional programming. We would use it on the scale of your adoption of functional programming and finding other solutions to using the languages that most of us use at the moment.
I'm a big fan of functional programming. How long have I got? I did a workshop on F# yesterday. The reason why I did it is because I've been playing with functional programming for years. I mean, I first studied them about 30 years ago, and I've been playing with Haskell, but they're not really very commercial. And I'd had F# in my peripheral vision for ages. And we decided to try and, in my present client, we decided to try and bring F# in and to see how it worked. And although it was a different way of thinking, I mean, we found that knowing C#, knowing .NET, was not very much help. But we also found that knowing Haskell wasn't much help either, because it's something entirely its own. And yet, what we found that once we'd learned a little bit of facility with this, we found that, first of all, we could write at 10 times the rate that we could in C#. We could write in 10 times, a tenth of the space that we could in C#. It was running between 5 and 100 times faster than the equivalent code in C#. It was quite slow to read, but I was absolutely amazed. This is an extremely performant language. And a lot of the performance comes from the fact that it's functional. And a lot of the performance comes from, ironically, the compromise that they've made to make it fit into .NET. So I am absolutely sold on functional languages, and particularly F#. And I've now found as a result of that exercise that it's now my go-to language. I mean, if I want to do a mashup, I'll do it. If I want to do something big, you know, things like compilers now, I will do it in F#. So I am a big fan of functional languages. What I notice is that functional languages are having a big effect on conventional languages. A lot of the clever stuff, you know, the lambdas and the link stuff that's going on in C#, it's there because of the F# project and because they needed that support in the runtime, in the IL. Otherwise, they couldn't have made it work at all. And everybody regards those things as being universally good things inside this object-oriented procedural space. And look at things like Python. Python is starting to grow object-oriented, functional concepts, and then being beaten down, and then growing up again and beaten down. But the thing is that this idea of functionalism, we have known for 30 years what the benefits are. It's just that it's been very difficult because you've needed to take this big step into the space to understand it, and a lot of people couldn't. But by trickling it into mainstream languages, then it's making it much more accessible and people can take time over learning it. And again, I believe that in 10 to 15 years' time, normal programming will be much more functional in flavor than it is now. And I think that pure procedural code is going to be in the minority, and it's going to be regarded as sort of almost like Visual Basic code was 10 years ago. No, seriously. So, big. Learn it. Definitely. Everybody learn it. Can't do without it. You'll be ahead of the curve. All right. Any more questions? All right. Thanks, folks. Coffee's downstairs. Noticed that the more bugs a program has in it directly correlates with the number of go-tos the program has in it. And he said go-tos cause bugs. This is his paper, the case against the go-to statement. And I'm going to explain more about what's in this paper because it's a short paper, but it's fairly heavy computer science. But what he did was he explained not just that this correlation is true, but he explained why it was true, and he explained what to do about it. Anyway, he sent this off to the CACM, which was being edited by Niklas Wirth, who was the guy behind Pascal. And Wirth said, great paper, lousy title, let's do that to it. And the rest, of course, is history. And you can look it up online right there. Now, what does he actually say? Because the principle behind this paper is actually pretty important. He said that when we look at a program, then what we describe on the paper, when you talk about a program, we talk about a thing, right? It's, you know, you can print it out on paper, or you can put it on a stick, or you put it on a server, or something like that. But we talk about it as if it's a thing, right? But what it actually is not a thing at all. It's something quite different. So what he said was that the program looks like a static map. It looks like, you know, it's fixed, it's on the paper, or it's fixed on the screen. But what it means is a dynamic process. It orchestrates all of the processing that's going on inside a computer somewhere. But it makes no sense to have a static program because the program inside the machine is inherently a dynamic thing. When we talk about a program, the language that we use is this sort of spatial static language. So we talk about right here, this line here, such and such has happened. Or what about this variable here, or this class over there? And even when we're talking about class structures which don't even correspond to things on the page, we will actually gesture into space and we'll say this class over here, and it's, you know, the data's moving like this. All of our language is spatial and static. And yet, the program has no concept of that at all. The program's concept is of time. The building blocks of a program inside the machine, the real thing that it represents, is actually a sequence of instances, one after another. Now, as people, as human beings, we are really good at understanding this spatial stuff. We're good at following maps, we're good at finding our way around cities. Compared to other animals, we're very good at it. So it's natural that we use this language. But as humans, we are really bad at understanding this. We all hate change, even if you don't admit it, you hate change. But you find that when you put people into geographies which are moving all the time, they get lost, they can't find their way around, they actually feel sick because people don't understand this sense of change. So what we're trying to do is control something which is inherently dynamic and changing, which we don't understand, using something which is inherently static and locational, which we do understand. And no wonder that's hard. So what Dijkstra said was this. If this has worked, yes, it has. He says what we need to do is we need to find some language. There's no point getting rid of this because this is how we think. But can we find some language in which we can express both of these concepts at the same time? He called it an execution coordinate. So he said, can we find something that we can speak about which not only has this static spatial feel to it, but even while it's static, also expresses this dynamism. And what he came up with was an execution coordinate. And the execution coordinate lies at the heart of what we now know to be structured programming. So let me explain this. Let's take a really simple program. Can you read this at the back? Because I normally have real problems with the projectors and being able to see this. What we have here is a really simple program. It's the kind of thing that you've seen time and time again. It's probably one of the simplest examples of anything that you're going to see at this conference. Now, we can look at it. This is, I'm pointing to it. I'm saying, here's the program. Here's line 13. I'm using this static language, right? But what we can do is we can animate this program. We can say what happens when it starts to move. And what we find is that it executes each line in turn. And as it executes each line, we have this sense of line, but it executes each line at some instant in time. What we've got along here is this time axis. So, and what we've got, what this picture shows us, is a correspondence between the location in the program. Can we understand that pattern in more detail? And it turned out that yes, we could. What we did next was we then drilled into our data in more detail. We said, well, can we find the bugs that were put there and were discovered at the moment they were put there? And can we find second-level bugs? These were the bugs that were introduced as a result of some other bug fix that was going on. And this is what we found. These primary bugs, they were about 90% of the total. The secondary bugs were about 99% of the total. Basically, what we saw was that our entire technical debt was being caused by one single anti-pattern. Now, I don't know how many of you have read The Mythical Man Month, Fred Brooks, absolutely classic book. One of the things that he says is that when people work on bug fixing, they find every team has about a constant bug rate. It might be one bug per 1,000 lines, one bug per 4,000 lines. If you're really unlucky, it's one bug per 50 lines, which is kind of what this was running at. But the point is, it doesn't matter how much fixing you do. This bug rate stays constant. And one of the things that he was asking was, well, is it because all of those bugs are already in there or because we're introducing them? Well, what this data showed us is because we were introducing them. Every time we fixed a bug, the nature of the bug fix introduced new ones. So pretty much 100% of our technical debt was caused by this one anti-pattern. I bet you want to know what this is. And I'm going to tell you, but not right now. First, did this work? First, we need to talk about this chap. This is Edgar Dijkstra. Edgar Dijkstra was a very clever chap. He was a computer scientist before there was even a word for computer science. And an awful lot of what we take for granted today, this guy invented. Back in 1968, he looked like this, much, much younger. And he wrote a letter. He was famous for writing these letters. He would send them off all over the place. They're all collected now in a library and numbered. But he wrote this letter, a case against the go-to statement. This was back in 1968, and he wrote it to the communications of the ACM. And in it, he said something which for the time was very revolutionary. He said, he has... Okay, I think we should make a start because we've got a lot to get through today. Can you hear me at the back? Is the sound reinforcement's working? Okay, good. This is a very big claim. I know this, and I know that I have to prove to you that I'm as good as my word. So I'm going to make you a promise. In the first 10 to 15 minutes of this talk, I'm going to convince you that this is true. It's going to take me the rest of the talk to show you how to do it, but I'm going to show you why this is true. That was a slide they made me put in. Now, let me tell you what the history is behind this, this talk and this stuff. I was working on a code base. This was a few years ago now, which was absolutely dogged with bugs. It didn't matter what we did with it. Every time we tried to knock one down, another one popped up. In order to try and take control of this was about 2.5 million lines, right? So it's not a major program. But in order to try and cope with this, we decided that we were going to delete our bug list and just see which ones popped back up again. Within 6 weeks, we had a list of 4,000. So that gives you an idea of what the problems were. So everybody was saying, how do we get rid of these bugs? And I thought, actually, there's a more important question to ask. Where are the bugs coming from? Not how do we get them out, but how are they getting in there in the first place? So this is what we found. This is basically the scale of the problem that we're working with. What we found was that when we looked at our bugs, when we went back through the version control, when we looked back at every fix, when we looked back at every bit of history, going back about 5, 6, 7 years on this whole project. It was a bit patchy in the beginning, but we had about 5 years of data. What we found was that the bugs fell into a certain number of categories. Basically, there was a bug pattern that kept on showing up over and over again. It was the same one every time. Now, there were some bugs that were there just because we hadn't understood what we were trying to accomplish, or there were bugs that we hadn't understood the frameworks that we were working with. But fundamentally, 90% of our bugs all were of the same pattern, all were of the same type. And they're all there because somebody was putting them in. And I thought, aye, that's interesting, and an instant in time. So in Dijkstra's terms, this is a good execution coordinate, because the one thing, say line 13, represents both the position in the program and that instant in time. So that works. Okay? Now, I want to explain in a bit more detail what his concept of an execution coordinate was. So we're going to animate this again, and we're going to stop it at line 13. So we've stopped our progress through the program, but we've also stopped our progress through time. We've stopped time. And we can see that we have this sense of being at line 13. So we can say, here is the location of here is where we are. Here's where we are in space, here's where we are in time. I'm sorry, I know I'm laboring this, but it's important. Now, print is a function. It's not merely something that we do atomically, it's got structure inside it. So what happens is, as we drill into that function, then we're climbing up the stack, we're finding other coordinates elsewhere in the program. This you understand. Your debuggers produce this all the time. You can see stack traces, you can see where you got to. But this was part of Dijkstra's idea of an execution coordinate. This is what you need. It's not just one number, it's this tuple of numbers, which says not just where you are, but it tells you the history up to that point. It tells you how you got there. We don't care about the history along here, because the only way to get to line 13 is through the intermediate lines. But we do care how we got to this point, because we can get to that point through lots of different paths. So that the execution coordinate involves that whole tuple. Does that make sense? As I say, this is not anything new. This is not anything that you haven't already seen before. This is what all of your debuggers give you. There's one more step that I want to show you, which is possibly a little less familiar. And that's what happens when you create a loop. Now, Dijkstra said, for reasons, for computer science and mathematical reasons, which I will tell you if you want, but is not worth going into now, he said we should treat these loops as if they are function calls. So we're not going round and round the loop. What we're doing is we're entering and exiting and exiting and entering and exiting the loop, like this.